Welcome again to the StarWind webinar. My name is Orest. I'm a solutions engineer here at StarWind, and today I'm going to guide you through how to build the StarWind infrastructure and what's most important to make sure it will be running on the maximum speed. And with no further hesitation, let's begin. Before we jump into the actual descriptions and our demo stance, let's make a quick look at today's agenda. So on today's webinar, we're going to understand the most optimal parts of the StarWind infrastructure, and namely the RAID configurations, the importance of networks, and how this should be provided for StarWind. We're going to take a look how StarWind VSAN for Hyper-V should be deployed, and correspondingly how StarWind VSAN for Vsphere should be deployed in the VMware environment. After this, we're going to have a quick Q&A session, and of course, in the end of our webinar, we're going to make the giveaway to our lucky participator and win the PlayStation 4 and the VR bundle. So the very beginning of the StarWind infrastructure performance questions should be started with a lower level, which the first one is the RAID and basically the storage settings. And it probably will be no secret that even the infrastructure that consists of the top hardware can be underperforming in case the RAID settings are not optimal. So that's why we need to start from the very beginning, and the first level here is the actual RAID settings. So StarWind recommendations for HDD-based servers are the following. For the RAID level, we support RAID 10 in terms of performance to make sure the HDD-based systems will deliver maximum read and write speeds. Read policy should be set to read ahead in order to boost the performance for sequential read operations. The write policy should be set to write back to increase the performance for sequential write operations. Also, we recommend setting the strap size to 64K, as according to our numerous and extensive tests, it is the most optimal setting that delivers the most optimal and maximum performance from the RAID array. Of course, for the SSD-based systems, the RAID settings will be different. In terms of the RAID levels, these are also more flexible in this case. So in terms of performance, StarWind supports RAID 1, for example, for 2 SSDs, RAID 5 for 3 SSDs, or of course more, and RAID 10, if there is such possibility, for 4 and more pairs of SSDs. Unlike with the HDD-based RAID arrays, we recommend setting the read policy to no read ahead, since there is actually no need in boosting the already fast sequential reads, and correspondingly the write policy to write through, since accordingly there is also no need to boost the sequential write performance on SSD-based storage. Now we're approaching the basically second and also very important level, which is the networking part. So StarWind VSAN itself is a hardware agnostic solution and has actually minimal bandwidth and latency requirements. So to start with, StarWind requires 2 network interfaces, one for StarWind synchronization and one for iSCSI traffic, can be also used for heartbeat, and one additional network interface as an additional heartbeat that should be located on a separate network card. As for the bandwidth requirements, StarWind requires minimum 1 GBE bandwidth, and the latency should be not higher than 5 milliseconds. Now, while these are the basic StarWind system requirements, StarWind itself can run on any other higher networking bandwidth, independent of the storage array itself. However, it is always advised and recommended to make sure that the networking part, the networking stack, will not be the bottleneck of the overall system performance. In this regard, iSCSI and synchronization should, first of all, have the same bandwidth. If iSCSI, for example, will have the higher bandwidth than the synchronization channel, the overall performance would still be bottlenecked by basically the synchronization bandwidth, since StarWind does the active replication. Taking this into account, there is no actual point assigning the higher bandwidth for iSCSI. In other way around, it is better in such a situation to assign higher bandwidth for synchronization. In this case, you will have actually the faster synchronization process. But of course, the iSCSI, which will be serving all the I/O operations, will have the other bandwidth. And of course, we do recommend selecting iSCSI and synchronization bandwidth depending on the storage. So for HDDs, we can start with 1 GBE and maybe 10 GBE will be enough for HDD performance for iSCSI and synchronization. Again, for StarWind, minimum recommendation is just 1 GBE. For SSDs, we recommend starting from 10 GBE and up to 25 GBE networking cards. Of course, if you can provide higher bandwidth, this is also valid. But of course, the main thing here is to avoid the networking layer bottleneck. For NVMe, we recommend starting from 25 GBE and up to 100 GBE bandwidth to make sure we also won't end up in the networking bottleneck for our active replication and overall system performance. Now, while we have gone through the, let's say, theoretical and the presentation part, we do not want to actually spend your time on the presentations, and we want to use it with the maximum efficiency. So I'm gonna drive you to our first Hyper-V setup with StarWind. So as you can see here, we have just pretty much the simple setup of the Windows Server 2019 Standard Edition. We already have prepared the Starwind installation and the settings, so I'm going to guide you on what we need and what should be installed also in order to save our time on the restarts of the system and of the actual configuration. So the first thing that we would need for our server and for failover cluster to function properly, we would need the appropriate roles and features. So these are the Hyper-V role. As you see, it's already installed, and correspondingly the failover clustering itself and the MPIO, which basically allows us to ensure simultaneous access to our iSCSI devices. Once these are installed, the other important thing is to actually enable the multipass for iSCSI devices. This should be added, otherwise we won't be able to make sure we can perform the concurrent IOs to our iSCSI disks. So once these are installed and added, we can then proceed with the actual StarWind installation. StarWind installation is quite simplistic, and here you can already see the StarWind already installed and our management console. So as you can see, we have our two servers already joined and the devices already created. But before we jump into the actual StarWind H8 device creation and provisioning, the third important thing is the networking stack. As you can see on our demo stand, we have just 3 adapters. One is designated for management and serves for our virtual switch. One is designated for iSCSI, and finally one for the synchronization. If we take a look at our iSCSI, for example, and synchronization channels, the first thing that you'll notice that they are configured with different subnets. This is the requirement in order to eliminate the networking overlap for iSCSI and synchronization traffic. The next important thing about the networking part is to make sure we can optimize our networking bandwidth and throughput. So in this case, we always recommend enabling the jumbo frames. So basically, the jumbo frame is an Ethernet frame with the higher payload than the standard MTU packet, MTU unit. By enabling jumbo frames, we can improve the network performance by making the data transmission more efficient. So we always recommend enabling these to 9014 in case of the Windows 7 environment, and these should be enabled on both of the nodes, meaning that both of our nodes in a simple two-node configuration should have totally symmetric network configurations. In this case, I'm not really going to disable the jumbo frame since it will cause the network restart of the networking port. So just keep in mind that for iSCSI and synchronization, we recommend enabling jumbo frames on both iSCSI and synchronization and on both of the nodes. Otherwise, if one node has the jumbo frames enabled and the other one does not, depending on the networking port purpose, for example, iSCSI or synchronization, it can cause issues with the synchronization or with the iSCSI channel's accessibility. Now, when we are already set with our networks, we are basically good to go with creating the StarWind H8 devices. So as you can see, we already have our Witness H8 device for just 1 GB created and one cluster shared volume device also created. These correspondingly are synchronized and active on both of the nodes. So to guide you through the process, we simply go to add a new device, hard disk, virtual disk device, provide the name that is convenient for you, for example, CSV2. 1 GB will be just enough for the demonstration purposes. And the next important thing, we require the dedicated storage for StarWind H8 devices. This can be either the separate volume or at least the separate partition from the system drive. The 4K byte sector size for the Windows environment, SIG provisioned. Currently, we do not configure RAM or flash cache in this demo stand, but you can always add the RAM in the write-back mode to accelerate both reads and writes, or in the write-through mode to accelerate only read operations. Correspondingly, there is the ability to add the flash cache that works only in the write-through mode, accelerating only the read operations. And simple enough, our first standalone device is created. The next thing we need to do is to actually replicate it to the partner node. We just select the partner node by the name or by the IP address. We select the heartbeat failover strategy for 2 nodes and create our new partner device. Again, we select the dedicated storage for StarWind H8 devices. It can be also set as an automatic storage in the StarWind settings from the beginning, and change our network settings. So in this case, we use heartbeat on the iSCSI channel, dedicated network for the synchronization, and management just as an additional heartbeat. and we select just synchronize from the existing device and create our replica to the partner node. And the synchronization process has started. From the very beginning, it runs the full synchronization. So the trick to do is to actually first create the 1 GB device and then simply extend your H8 device to the required size, as this does not require any service interruption. And the size has been changed. Now, the next important thing is to actually provide access to our StarWind iSCSI devices. So for this purpose, we go to the iSCSI initiator. As you can see, we have already discovered the local path and the iSCSI dedicated network to the partner node. Correspondingly, we can see our targets already connected. So now let's proceed and connect our new cluster shared volume. So this is the CSV2. It's connected from the local node. Enable multipass. The local adapter is Microsoft iSCSI initiator, and we select the target loopback IP address. Now, before we proceed, I'd like to pay your attention that this part is extremely important when we are talking about the performance. First of all, we recommend assigning two loopback IP addresses for the cluster shared volume devices. However, this depends the overall number of the iSCSI connections. Highly depends, first of all, on the actual iSCSI bandwidth and, of course, on the system CPU power. So for 1 GB and 10 GB bandwidth, we recommend assigning two loopback connections and one partner connection, just as you can see here. Enable multipass and just one partner connection. For 25 GB bandwidth and higher, we recommend configuring two loopback and two partner connections, and starting from 40 GB and above, we can consider also adding the additional loopback address and the additional partner address, totaling in 3 loopback addresses and 3 partner connections for 40 plus GB bandwidth. However, as I mentioned, the CPU power is extremely important, and the optimal number of the iSCSI connections should always be measured with the performance tests. Now, the additional number of the iSCSI connections always uses more CPU resources. So while one might eventually think that adding more loopback or partner connections will be better, in fact, it may actually end up with the maxing the CPU resources and ending up in lower performance than the lower number of the IP addresses or local and partner connection would actually result. This is extremely the case in the cloud environments where different instance types provide different CPU resources, namely the number of cores. So in that cases, it might be even more efficient to simply assign one loopback address and one partner connection just to minimize the CPU overutilization, which eventually, again, would end up in high performance rather than adding several loopback and several partner connections. So again, the StarWind let's say the average recommendation is to assign 2 loopback and 1 partner connection for 1 GBE and 10 GBE network. But again, depending on the environment, it always should be tested with a different amount of iSCSI connections for both local and partner, and determining which configuration provides the optimal performance. Now that we have done this on the first node, let's switch to the actual second node and connect our iSCSI targets also on this side. So as you can see, we have just the symmetric configuration, also the loopback IP address and the partner iSCSI connection. Let's just refresh. And here is our partner cluster shared volume. So we'll just make 1 partner connection and 2 local connections for our local target. Now, you may notice that the only one device that is left inactive from the partner node is the witness device. We always connect the witness by a single loopback IP address, since it is always faster to grab the local witness device in case of the failover, in case one of the nodes fails. The same thing you can see on our first node. So the partner witness device is disconnected and only the local witness is connected. The next thing that also impacts the system performance is the actual MPIO settings, basically the multipassing. So there are various options with the Windows 7 environments to choose our MPIO load balance policy. So failover only policy is used to provide additional availability in case one of the connections fails. So one connection is active, the other one is in standby, but it does not provide the load balancing or network aggregation as such. Next one is the round robin, and it's the default settings for most of the connection. It basically aggregates the network connections and sends data equally across each connection. The next one is the round robin with subset, which is basically a number of passes added just as an additional failover adapters, which will be only used when each member of the round robin primary group has failed. The next one is the least QDEPs. Now, this policy also provides the aggregation of passes, but sends each IO request through the connection with the least number of requests in the queue. The next one is weighted pass. It also provides the form of aggregation, but adds the ability to manually assign weights to different passes. These weights will basically determine how heavily each connection will be used in comparison with the others. And the final option is leased blocks. It's quite similar to the least QDEPs in that it unevenly distributes the IO requests. However, this policy, unlike QDEPs, sends each IO request through the connection with the least number of pending IO blocks. Now, the StarWind recommendation is to set the least QDEPs load balance policy for our cluster shared volumes. As in most of these scenarios, this is basically the smartest way of utilizing our local and partner iSCSI connections, and as well as the result, achieving more and maximum system performance. Now let's do it also. Let's check the partner device. It has accordingly also changed to the least QDEPs. For the witness, we assign only the failover only policy, since there is just one active connection and it makes no actual sense putting it to the other load balance policy. And the same should be performed on the partner node. Changing to least QDEPs and making sure that our local witness is also set to the failover only. Now, after we have added connections to our iSCSI devices, we can actually form them. So this is simply done through the already common disk management. And we can see our new one. Let's bring it online, initialize it with GPT, and create a new simple volume. Assign the drive letter. Also, please note that we do not assign the drive letter for the witness disk. We can specify the convenient naming here and just wait for it to finish formatting. Now let's just go to the partner node. We scan our disks and just bring the new device online. Now we are approaching the actual failover cluster configuration. So once the failover cluster is set up, so you can see we have our two nodes already connected to it. We can then proceed with adding disks to our failover cluster. So one device accordingly is already serving as the cluster shared volume, and the witness disk is already serving for the cluster quorum to make sure we are still able to serve the production in case one of the nodes goes down. So now we can add our new device and also add it to the cluster shared volumes. And let's make a convenient naming for it. Now, the final part that will actually influence the system performance is the networking used in our failover cluster. Now, if you pay attention, we can have the different usage for our iSCSI management and synchronization channels. Now, let's start with the actual management interface. As you probably already know, the management interface will serve for all the cluster network communication and, of course, the client access. For the iSCSI and synchronization, the question is a bit different. We recommend to minimize any other network traffic, basically lead it to zero on the actual iSCSI and synchronization channel. For synchronization channel, however, we can leave the cluster network communication, but without allowing clients to connect over this network. Now, this is the basic recommendation. However, this always depends on the workload of your system. If the workload is intense, we would recommend to disable any other usage of the iSCSI network and put the cluster communication and clients access on the management. However, if the system workload is not that intense, we can also use iSCSI for additional purposes, for example, for cluster network communication on this network. But again, this always depends on the system workload, and it's most optimally set to the performance tests and dedicated time and benchmarking of the system performance with different networking settings. And for the actual live migration settings, we use the management and the iSCSI networks. For live migration, for management, we put it to the top priority and iSCSI to the lower priority. So just in case we could still run the live migration of our VMs, even in case one of the channels will fail. Now, since we covered the Hyper-V scenario, let's further move on to our Vsphere stand. Now, just as in case with the Hyper-V, we also have here a two-node setup. Both of our ESXi nodes are already joined to the cluster and to the data center. We have StarWind already installed on each of the ESXi node. Now, StarWind, in case of the VMware, is installed as the Linux application from the OVF template. So basically, if we go to our host, we just need to deploy the OVF template, locate the required file, and here we can already see the extracted OVF files from the archive and just need to start the deployment process of the virtual machine. Now also let's start from the very beginning in case of our Vsphere scenario. Just as in the Hyper-V stand, we also have just 3 physical adapters in our environment. One serves for the management purposes, one for iSCSI, and one for synchronization. So as you can see, one physical port is provided for the management, one is provided for the actual iSCSI. For iSCSI, we require one VM kernel and its port group, and the additional port group that will provide access to the virtual machine for the iSCSI port. And of course, its dedicated standard virtual switch. Again, if we take a look at our settings, you can see that we have Jumbo frames enabled here, and of course, enabled on the VM kernel itself. And of course, this should be symmetric on both of our nodes. Both on the virtual switch and on the VM kernel. Now for the synchronization, we have the additional dedicated physical adapter with its own virtual switch and just a single port group to provide the physical adapter to our VM. We do not require the VM kernel for synchronization since it will not participate in the actual I/O operations. Now, if we check our StarWind VMs, you can see that we correspondingly have our management network, iSCSI, and synchronization provided correspondingly with the VMX Net3 network adapter type. The other important thing about the performance in case of the Vsphere is the actual provisioning of the disks inside the StarWind VMs. Now, there are several options for those. The first one is to provide them as the VMDKs, just as you can see it in this scenario, from the local VMFS data store. In this case, we highly recommend making them SIG provision eager zeroed to eliminate the unnecessary and additional read, modify, and write operations that are typically occurring with the SIG provision lazy zeroed or moreover with the SYN provision disks. The other option is to RDM the disks to the StarWind VM, basically the raw device mapping of the disks, or the most optimal approach in terms of performance to pass through the entire RAID controller to the StarWind VM. Correspondingly, in this case, StarWind VM has to be installed on the separate storage and the rest of the RAID controller could be passed through inside of it. This will eliminate the additional VM decay layer and significantly improve the performance. And of course, our configurations are the same on both of the StarWind VMs. Same management, iSCSI, and synchronization connections, and the hard disk, basically the VMDK in our case for this lab, is with the SIG provision EGR0 type. Now, once everything is set on the primary VMware level, we can then proceed with the configurations inside our StarWind VMs. So let's log in, and I already have it there. The default root password and username, and we end up in our web interface. The overall system performance metrics are provided here, the logs information, and storage and networking tabs is where we actually configure our storage and the networking. And again, let's start with the networking part. So of course, for our management, iSCSI, and synchronization connections, we highly recommend setting the static IP addresses with the DNS connections for the management channel, and for iSCSI and synchronization connections, also static IP addresses in different subnets, but with no need for connection to DNS servers. Correspondingly, the same settings are on the partner StarWind VM. The next level here is the actual storage. So once we have our VMware virtual disk withable, it is just 40 GB. We just format it with the XFS file system and mount the disk. Now there is also the part of optimization that can be done on the Linux side. Now, in case of StarWind Virtual SAN for Vsphere, which as you can see is delivered as the Linux-based VM, there are several settings we can improve to make sure our system will perform optimally and with its maximum speed. The first thing here to be done is the actual I/O scheduler inside the Linux. So for this purpose, first to check which settings are available at all. So we can see that the I/O scheduler has been set to NUP for the SDB disk, which is our VMDK used for the StarWind H8 storage. Now, there are several different I/O scheduler options, as you can see. So what actually is the I/O scheduler? It's basically a way to optimize the disk access requests. And this is traditionally achieved by merging I/O requests to similar locations on the disks. By grouping requests located at similar sections of disk, the drive does not need to perform additional seek operation that often, and improving the overall response time from the disk operations. As you probably noticed, I mentioned the seek time and the rotation. So yes, by default, these are enabled for the HDD-based arrays. which of course is not the same as for the SSDs. So by default, for the HDD-based arrays, the CFQ option will be applied, which is basically the IO scheduler that works by creating a per process IO queue. The goal of this option is to provide basically a fair priority for the IO to each process. This is specifically designed to reduce the disk sticking time, and it groups basically the IO process queues in the round-robin fashion. However, it cannot be the well enough option for the SSD-based storage. For the SSD-based storage, we recommend the NUP scheduler option, which is basically quite unique. So rather than making any sort of prioritization for IO operations, it simply places all IO requests into a first in, first out queue. And while this scheduler does try to merge similar requests, that's basically the extent of the complexity behind this scheduler. So basically, it drives all the IO further to storage with no additional efforts to perform the intelligent grouping to reduce the seeking time. And this policy is the most optimal for the SSD-based configuration. The third option is the deadline. The deadline scheduler works by creating basically two queues, a read queue and a write queue. Each IO requests in this case has a timestamp associated that is used by the kernel for the expiration time. So for SSD, the basic recommendation would be to use the NUP IO scheduler option. For HDD-based arrays, we recommend using either the default CFQ or deadline, also to optimize the requests for read and write operations and squeeze perhaps more read performance from what the HDD can actually deliver. But again, these options in the perfect scenario should be tested and picked towards the individual systems. And the additional policy that can improve the overall system performance is to actually set the no read ahead policy for devices. And this is also done simply by just executing the proper command. I won't be making the significant emphasis on the commands themselves, as we already have the knowledge base article prepared on this, so you'll be able to find all the detailed commands in the Linux environment right there. Now, after we have optimized our settings and configured our storage with the XFS file system and mounted, we can then proceed to the actual configuration and creation of StarWind H8 devices. Just as in the previous case, the actual H8 devices creation process is performed through the StarWind Management Console, which is currently installed as the application on top of any Windows-based machine. So again, you can see our two VMs already joined. One H8 device is already created and provided further to the Vsphere cluster. So as in the previous case, let's also create one more H8 data store. Let's make it to data store 2. Again, 1 GB size. Here you can see our mount point for disk 1. $512 for VMware native bytes sector size. Again, SIG provisioned. RAM and flash caching options can be enabled optionally, and create our device. Next, we just need to replicate it with a synchronous two-way replication. And there is the IP address. Heartbeat failover strategy for 2 nodes. Create new partner device. The location on the partner VM. And our networks for the heartbeat, for synchronization, and for the iSCSI. So as you can see, the management channel sets the additional heartbeat, iSCSI also as the heartbeat and dedicated synchronization channel. Now, why I am also showing you the process of creating the additional devices in both Hyper-V and VMware environments is, first of all, because we recommend creating 2 H8 devices. Of course, you can create the single H8 device for the entire capacity, but if possible, we still recommend creating 2 or more H8 devices to ensure concurrent I/O access from our nodes. And also, in case of the VMware environment, this also allows us to configure the data store's heartbeat for the vSphere. And the synchronization process is finished, just 1 GB device. And now we can proceed to our vSphere cluster. And let's go to our iSCSI initiator. Of course, before connecting the devices themselves, you'll need to add the iSCSI software adapter. This is done simply by adding the iSCSI software adapter. It's already grayed out since we already have one on each of the nodes. And then by creating by assigning the dynamic IP addresses, the local virtual machine and to the partner virtual machine. Now we can see that we have our 2 devices connected. One is already consumed by the created VMFS H8 data store, and one is left not consumed yet. And we have the total of 4 active passes. Now in VMware environment, there are also different settings for the pass selection policies and for the actual MPIO. There are 3 of them basically. The most recently used, which selects the first working pass discovered at system boot, and it's the default policy for the newly created devices. If the most recently used pass becomes unavailable, the ESXi host will simply switch to the alternative pass and continue to use it while it is available. Also, there is no failback in this technique. If the original pass which has failed comes back online, ESXi host won't use it back again. This is the default policy, again presented from the LANs from the active passive arrays. The fixed policy is where ESXi host uses the designated pass, if of course it has been configured, and otherwise it uses the first working pass discovered at system boot time. If the ESXi host cannot use the preferred pass, it selects a random alternative available pass. And unlike with the most recently used, the ESXi host automatically reverts back to the preferred pass as soon as the pass becomes available. And the final option that we use is the round robin. In this way, ESXi host can use all available passes and thus enabling load distribution among all the configured passes. This can be also used and for active-active or active-passive type of storage arrays, and precisely for StarWind with active-active replication, this is the most optimal policy. This is also the most optimal policy in terms of the performance, since the round-robin algorithm also allows us setting the IOPS limit. Now, round-robin path selection policy uses the round-robin algorithm to balance the load across all active storage passes as mentioned. A pass is selected and then used until the specific quantity of data has been transferred. After that quantity has maxed out, the next pass is selected in the list. And the default IOPS limit in this case is 1000. So in this case, the new pass is selected and used only after 1000 IO operations are issued. So adjusting this limit can provide the optimal impact on the performance actually by improving it, and is actually what is recommended by StarWind to set the IOPS limit to 1. So in this case, the pass switching will be activated after each single IO operation, which will also allow us to utilize our networks with maximum efficiency and thus increasing the system performance. So you can see that the passes have already been activated for the round robin. One of the options is to select the actual iSCSI disk and then edit its multipassing and set to the round robin, but otherwise it is already set by our VSAN script. So once we have our storage connected, the next important thing is to run the actual StarWind VSAN script, which first of all sends the option to automatically discover and connect the passes after the StarWind service start or restart. And additionally, it already automatically sends the round robin limit for the IOPS to 1. So you won't need to do this manually. To configure the rescan script, you'll just need to go to the StarWind folder and locate our HB rescan script. I'm personally doing this with the Midnight Commander, as I'm finding it the more convenient way for me. For this rescan script, we'll just need to use the ESXi host IP address, ESXi user, and the ESXi password. Once set, we just need to make sure that the rescan script operates properly. And once executed, it will automatically change all the passes usage to the round robin, so that again you won't need to do this manually for each device. The other good way to check if the StarWind HBA rescan script is really working is to actually go to the ESXi host and check the recent tasks and events, since these are not displayed in the actual vCenter. And as you can see, the recently executed rescan all HBA adapters and set multipass LAN policy has been accomplished successfully. The same should be set on our partner StarWind virtual machine. Now, after the round robin has been set to 1 and our actual iSCSI devices are connected, we can then proceed with creating the data store on top of our H8 device. Now this one throws the alert, so don't get worried, adjust for the amount of the free storage left on it. And we can actually create the new data store. The VMFS type, let's name it accordingly, StarWind Data Store 2. Select our newly created iSCSI disk and use the available storage. Oh yeah, and this is the good case again to show the extension of StarWind H8 device. So let's add 2 more GBs. The resultant size will be 3. Executed on both of the nodes. So let's do the process once again. I hope it will grab, it had not yet grabbed the size correctly. So let's just do storage rescan. Okay, good. Let's run it on both of the nodes. Now we have the correct size and should be go to create our new data store. So again, StarWind Data Store 2, our iSCSI disk for 3 GB, VMFS 6 type, and create the actual H8 data store. As to the additional tweaks for our system performance and optimization, we also recommend setting the max disk max IO size to the 512. So basically, many applications are designed to issue large IO requests for higher bandwidth, but for certain applications and for several storage devices, it has been found that actually decreasing the size of the IO requests may actually deliver better system performance. So in this case, we would need to go to our E6i nodes and change disk max IO size. Now let me just mark myself where it's done. And yes. Now to our advanced settings, and let's actually filter this by max IO, and here we can change the default value to 512. Accordingly, the same should be done on the partner node. And okay, once this is done, the last thing to make sure and to do that our H8 cluster will perform as required is to enable the Vsphere H8. As you can see, it is already enabled, it's turned on, and it's basically the feature that is responsible for restarting the VMs in case of the host's failures.